Hello, everyone. Welcome to the Space Telescope Public Lecture Series. Today's talk will focus on neutrino astronomy, a new window into the extreme universe. Our speaker today is Dr. Marco Santander from the University of Alabama. My name is Dr. Quinn Hart, and I'm a Senior Education and Outreach Scientist in the Office of Public Outreach at the Space Telescope Science Institute in Baltimore, Maryland. Your regular host, Dr. Frank Summers. He's taking some well-deserved time off, so I'll be your host tonight. We couldn't run this lecture series without the support of our other regular public lecture series team, Thomas Marufu and Grant Justice at Space Telescope, who make sure that all the technical details for these events are running smoothly. This is why we can bring this talk to you virtually in real time and as a recording if you're watching at a later date. Well, what are some of the upcoming public lecture series talks? Well, next month, when Dr. Frank Summer returns, he will be your host and he's going to be your speaker. He'll be talking to you about Eta Carinae, a massive star that has some major past explosions that might appear like they're supernova-like, but really aren't, and create some amazing nebular features surrounding it. In June, the talk will focus on how we understand the formation and evolution of galaxies by Dr. Cameron Hummels. Now, we don't have a talk in July, but we anticipate that the commissioning of the James Webb Space Telescope will be concluded, and we will see the highly anticipated release of the first science images from the telescope. So we're planning a talk in August that will focus on these first observations from Webb. To learn more about today's talk, these upcoming talks, you can go to our website where you can find our links to the webcast. Our website is www.stsci.edu/public-lectures. You will find links to our webcast, and you can subscribe to our mailing list to get the talk announcements so you don't miss a thing. If you scroll down on that page, you'll see the list of the upcoming lectures that I just referenced, but you can also find links to all of our past lectures here as well. Now, if you click on read more for any of the talks, it will bring you to a dedicated page where you will find the talk information, including the title, the speaker, and a description of that talk. You will find the links to all the recorded talks either through the STSCI webcast or through the YouTube channel here. So welcome to those of you who happen to be listening to a recorded version of this talk. For our email list, you can sign up on the Public Lecture Series webpage on our website. You can also subscribe to our YouTube channel, which is youtube.com/Hubble Space Telescope, where you will get new video notices and reminders of live events to come. You can also send any comments or questions about the public lecture series itself to publiclecture@stsci.edu. Now, if you want to follow us on social media to learn more about what's going on in the universe, we have social media accounts for Hubble, Webb, and Roman, and STSCI. The Facebook pages names are there: Hubble Telescope, Webb Telescope, NASA Roman, and STSCI. We also have Twitter accounts where you can follow along on the news of the day, learn some more in-depth science, see news, press releases, variety of things. See a lot of threads on science like spectroscopy, for example. So our Twitter handles are there: at Hubble Telescope, at NASA Webb, at NASA Roman, at Space Telescope. On YouTube, if you're watching on YouTube, you're already on our channel, Hubble Space Telescope, and you can also look at NASA Webb Telescope. And then we're also on Instagram at space_telescopes and NASA Webb. So plenty of opportunities to learn about what we're doing over here with the public lecture series, but also ways to learn and keep up to date on what's happening in the news. So speaking about the news, let's talk a little bit about some interesting things that are happening since Frank last talked to you last month. So news from the universe. Now, I'd like to continue what Frank continued last month, which is giving you some Webb updates. So Webb has had a major alignment milestone, and many of you may have already seen this image, but if you have not, This is a telescope alignment evaluation image. Now, last month, Frank showed us that the 18 images of a star was imaged with Webb. That's because the 18 hexagonal mirrors that make up the primary were not aligned yet. So you saw individual images. As the engineers began to move the mirrors, very fine movements, they were able to stack the images to create one star image. But that stacked image still needed to be sharpened up. So in mid-March, the mirrors were successfully aligned with one of the instruments on Webb called the NIRCam instrument. And that's this is how this image was taken, was with that instrument. This star has a very long set of code names. It's 2MASS J17554042 plus 6551277. And you might be asking, that's a really long slew of numbers, and it's basically the coordinates of the star of right ascension and declination. The image used a filter at 2 microns in the infrared, and it's colorized in this red to optimize the visual contrast. This beautiful engineering image shows us that the optics on the telescope are aligned with the NIRCam instrument. Again, this is a major milestone for the telescope because every optical parameter of the eyes of the telescope has been checked out, and it's performing at or above expectations. It's just spectacular. It's beautiful to look at when you say. Now, again, this is crucial in order to start future science observations after the telescope's full commissioning has concluded. Now, one thing that pops out at you may be that the diffraction spikes on this star taken by Webb looks different than the diffraction spikes on the Hubble Space Telescope. There are 6 major spikes on the Webb image, in contrast to the 4 spikes you normally see with a Hubble star, which you see on the right there of a variable star RS Puppis. The difference here is related to the shape of the primary or the main mirror on the telescopes and the struts that hold the secondary mirror. The JWST diffraction spike is a result of the edges on the outside of the segmented mirror that uses a hexagonal mirrors, individual mirrors. And the other minor feature is specifically in the Webb image, the one that goes across, that's kind of faint horizontally, that's related to the support structures for the secondary mirror. Now, the other amazing image that really caught at least my eye was looking at all the detail in the background of that star, seeing all those specks. Those are galaxies. Now, this image exposure time here is 2,104 seconds, so it's about a 35-minute exposure. It's really fun following some of the scientists on Twitter, going around looking for previous images of some of those galaxies and matching up to Webb. So for those of you who have some free time on your hands, definitely go check that out. Now we can compare the selfie images that were made with the NIRCam instrument. On the left, you see the selfie when NIRCam was completely aligned to the optical elements of the telescope. Notice that every mirror appears uniformly illuminated. That's part of the alignment process. On the right was the first mirror selfie where each individual mirror had not been aligned yet. And so you only saw one of the mirrors actually pick up light that went into the camera. So again, that was pre and post full alignment on NIRCam. Now, what's next? Well, right now is the multi-instrument, multi-field alignment process. The telescope alignment for the other instruments started after that first alignment with the NIRCam instrument. As of April 1st, the fine guidance sensor, so this is on the observatory here. So NIRCam is aligned with the mirrors. The fine guidance sensor, the near-infrared slitless spectrograph, and the near-infrared spectrometer have all been successfully aligned with the observatory. In the weeks to come, the instrument there on the upper right-hand side is MIRI, the mid-infrared instrument. It's still cooling down with active cryogenic cooling techniques to reach an operating temperature that's just below 7 Kelvin, quite cold. Then the telescope optical alignment can begin for that particular instrument. When that's successful, there'll be a key meeting will be called to confirm the end of all this telescope alignment. And then the instrument commissioning can begin so that we can get ready for science operations, which can start in the summer. So there are exciting times here to watch and to hear about all about this amazing telescope gearing up to start studying the universe in unprecedented ways. So our public lecture series will keep you informed as the results come in. So stay tuned. Another piece of news from the universe here is Hubble has broken its own record and has spotted the faintest star ever seen. So how's it possible to detect a star so distant that we're looking so far into the vast? So what you see here on the left is a large view of a galaxy cluster, WHL 0137-08. It's a collection of hundreds of galaxies bound together by gravity. Now, most of the cluster mass is actually in dark matter, but when you take all the mass, that dark matter and the regular matter, it warps or bends the fabric of space-time. So any light source behind the cluster that passes through the cluster can appear stretched out or warped too, and it also can magnify the light. This is called gravitational lensing. So when we are seeing the light from a star nicknamed Arundel, it appears, now what I'll do here is zoom in a little closer to a small section of that image, and you'll notice this reddish colored arc. And this arrow here is pointing to that furthest star that has been seen, named Arundel here. The light has been traveling through the universe to get to Hubble for the past 12.9 billion years. So just about 1 billion years after the Big Bang. And again, this was possible due to a special set of circumstances. So let's break that down really quickly. So when we take again, look at the close look at one of these warp features, you can see a series of dots. The one dot that's pointed out there is that really distant star. The warp features here happen to lie along a line of maximum magnification called a caustic, and the star's brightness also increased 1,000-fold, which is why we can see it at such large distance, due to this very perfect alignment with the cluster in the foreground. The detection surpassed the previous star distance record by Hubble. That star is located at a distance so that we're peering back only 9.8 billion years into the past compared to 12.9 billion years here for Arundel. The previous record holder was also detected by a gravitational lensing effect by a foreground cluster of galaxies. Now, my area of research in the past has been clusters of galaxies. It's near and dear to my heart, so I love seeing these images. Now, it's really important to find these ancient stars because their properties give us clues into star formation when the universe was really young. How massive were they? How bright were they? What were they composed of? Was it mostly traces of hydrogen and helium from the beginning of the universe? Did they already have heavy elements like carbon and nitrogen? So researchers will continue to study Arundel with the James Webb Space Telescope to uncover more details and give us some more answers. So that's the news that I wanted to share with you today. And now we'll move on here to, I'd like to introduce to you our speaker. So again, tonight we're going to be hearing about neutrino astronomy, a new window into the extreme universe, Dr. Marcos Santander from the University of Alabama. So let me stop sharing my screen here. Okay. And I'd like to welcome Dr. Santander to the public lecture series here. Marcos was born in the province of Mendoza, Argentina, near the Andes, a region that is best known outside of the country for its wine production, Malbec in particular. And I can attest to the wonderfulness of Malbec because I had a bottle this weekend with friends. Now, he earned his bachelor's degree in engineering from the National Technological University in Argentina. He moved to the University of Wisconsin-Madison to pursue a PhD in physics, working on the IceCube Neutrino Observatory. He graduated in 2013 and moved to Barnard College, Columbia University, for a postdoc in gamma ray astronomy until 2017, when he joined the faculty at the University of Alabama as an assistant professor. Since then, he leads his research group on the study of neutrino and gamma ray emission from some of the most powerful objects in the universe. When not thinking about high energy astrophysical sources, he also enjoys astronomy as a hobby, looking through his backyard telescope. Beyond astronomy, he enjoys photography, playing guitar, watching Argentine soccer, and most of all, spending time with his daughters, Florencia and Emma. So let's give a warm welcome to Dr. Santander, and take it away when you are ready.
Okay, thank you very much, Dr. Hart, and it's really a pleasure and an honor to be here talking to you. At this institute that's meant so much for my formation, as even though indirectly, as you will learn later on. So I'm going to be talking about neutrino astronomy, and perhaps that's a new topic to this kind of lectures. And I will try to motivate that as a new way of looking at the extreme universe. And when I talk about the extreme universe, I'm talking mostly about the highest energies that we can observe from our vantage point in the universe. And so for the last few centuries, we've been doing astronomy mostly with visible lights, for the last 300 years or so. But in the 20th century, with the development of electronics and also with the development of new sensor techniques, we've been able to expand that window into the universe into other wavelengths that are not visible to the human eye, all the way from radio with radio telescopes, going through microwave, and of course I have to mention JWST and Hubble as the darlings of the institute, going to higher energies in tundra and gamma rays, for instance, with orbiting satellites and also ground-based telescopes. And out of the entire electromagnetic spectrum that spans many energies, many orders of magnitude in energy, we only see a sliver of that with our own eyes. And therefore, we want to expand that, especially pushing it towards the higher energy. And in this case, in this electromagnetic spectrum, what you're seeing here, the photon energy increases to the right. Okay, so we're going to try to push even further to the right to try to reach the highest observable things in the universe. And why do we do that? Because we kind of study different phenomena in the universe by looking at them in different energies. And just to show you kind of an illustration that each one of these telescopes has a different sky to look at, I wanted to kind of use an example for something that you can see with your own eyes. For instance, the Big Dipper is an asterism in the northern sky. And if you look at it on any given night, if you're in the northern hemisphere, you will see that what makes this are discrete point sources of light, right? And of course, we identify those as stars. That's not surprising. But if we wanted to look at this at very high energies, let me show you the same patch of sky, but looking at it in gamma rays with the Fermi Space Telescope. So this view now is shown only in gamma rays. The colors here indicate different gamma ray energies, and it's the same patch of sky. I haven't changed anything in the coordinates. So if you flip back and forth, you'll notice that there's nothing that resembles the Big Dipper in this part of the sky. And the reason for that is that now these point sources of light are not longer stars. They're actually supermassive black holes at the distance of at the center of distant galaxies that are accelerating particles and are shining in gamma rays. For instance, this particular one is 8.2 billion light years away. So that kind of tells us that if we wanted to look at very high energies, you have to use a different type of telescope, and that will tell you about something else in the sky that you may not be able to see with just visible light. So we want to keep pushing in that direction towards higher energies. Okay, so you would say, okay, we have this great view of the sky with gamma rays. Let's keep pushing there. Let's keep looking at even higher energies in gamma rays. But there's unfortunately an issue with gamma rays, is that at some point the universe actually becomes opaque. There's remnant light from the first generations of stars. There's also remnant radiation from the from the Big Bang, called the cosmic microwave background, and that actually acts as a fog in the universe that prevents the propagation of gamma rays over very long distances. So at energies that I'm going to measure in units of electron volt, is perhaps not a very popular unit of measurements for energy of photons, but just to give you an indication of what we're going to be talking about, the light that we see with our own eyes has an energy of about 1 electron volt, okay? So when I show here things that have 1 mega electron volts, meaning 10 to the 6 or 1 million electron volts, that means that that light has energies of about 1 million times the energy of visible light. Very well, so as I mentioned before, I want to keep pushing to the right in this kind of a plot so that I can see things with higher and higher energies. And as you can see here, this kind of blue blob is showing me where I can no longer see into the universe because the universe becomes opaque. And at energies of about 10 to the 15 electron volts, 1 peta electron volt, I cannot even see all the way to the galactic center. I mean, you can go out in the southern hemisphere, look at Sagittarius, and you will see kind of the group of stars in the night sky that are kind of towards the galactic center. But you cannot do that with this very high energy gamma rays. And therefore, we want to use something else to really explore the highest energies observable in the universe, really to look not only high in energy, but also very deep in the universe. And let me put together kind of what I will think would be the ideal messenger from the high energy universe if we wanted to put together a particle that can transmit that energy, that can transmit that information from these sources. I would say that they would have to be neutral, electrically neutral, because charged particles are bent by magnetic fields. And we know that there are magnetic fields in our galaxy and also between galaxies, and therefore their paths are bent. And we cannot do astronomy like that, because by the time they reach you, those charged particles would have traveled on kind of a wandering path, and they will not point back to the source, which is a kind of a requirement for true astronomy. So they would have to be electrically neutral. They will also have to propagate over long distances without decaying. There are many particles out there in the kind of the in particle physics that are neutral, but they decay very quickly. And we want that these particles don't decay while they're traveling to us, otherwise we'll lose that information. We also want to have a low probability of being absorbed so that nothing in between that source and us can block that information. And finally, we want them to be unique, because we already have a view of the high energy sky already to some extent from light alone. But we want that information to provide kind of a complementary view of the universe that we can join together with photons, so that they can provide a different type of information. So with that wish list, you look at the particles that are out there in particle physics that are known, and actually there is one that works great, and that is the neutrino. Okay, so I will introduce very briefly the neutrino. So neutrinos are neutral particles. They're elementary particles, and they have a very low, very small, but non-zero mass. Okay, so as far as we know, they're elementary particles, and they were first proposed in the 1930s, and but they were first detected in 1956. And that delay between proposal and detection has a good reason once I tell you a little bit more about them, why they are so hard to detect. What are some of the sources that produce neutrinos that we know of? We know that they're producing radioactive decays, both on the ground, on the rock, and even in nuclear reactors. And here you have a map of neutrinos being produced by the rock in our planet, but also by nuclear reactors. So on top of just the exposed rock of the planet, you will see that some parts of the US and some parts of Europe are very dark, and that's mostly because there are nuclear reactors there that emit many neutrinos. Even a banana is a neutrino emitter. There's potassium 40 in the bananas, and they decay, and about a regular sized banana will have about 14 neutrinos emitted every second. And as you may notice, you don't see anything coming out of them, and that will become clear in a second why that is. The sun is perhaps one of the strongest sources of neutrinos we know of, is the strongest one that we can detect. And this picture that I'm showing here is a picture of the sun, not taken in light, but taken in neutrinos, figuring out where the neutrinos were coming from the sky, and they point back to the sun. Every second, every square centimeter of the Earth is swept by about 100 billion neutrinos coming from the sun. And as you can probably tell by looking at this presentation, nothing happening right now. They cannot be, I mean, this cannot be noticed so easily, but we'll talk a bit more about why that is. And so far, beyond just the sun, we also know at least one more source that was detected in 1987. That was a supernova. Is the death of a massive star where there is a core collapse, and therefore in that core collapse there are particle interactions that lead to a very large emission of neutrinos. So what you see here is a detector that was operating in Japan in the mine of Kamioka, and the x-axis shows time, and you see that overall the detector was detecting events at a certain rate, and there was a huge spike. So that was when the the plane of neutrinos coming from that supernova that happened in the Large Magellanic Cloud swept the Earth, and we were able to detect several of them. Okay, so most of these neutrinos that I'm mentioning here, the ones from radioactive decays, the one from bananas, the one from the sun, and the one from the supernova 1987A, have energies of about 1 million times the energy of visible light. So what about 1 MeV, right? Mega electron volts, which means 1 million times that. But we want to go even further with that. So I will say a little bit more about neutrinos because they're important to understand why it's so challenging to detect them. As I said, they have a very small mass, is non-zero. We haven't been able to even measure it, but we know it's non-zero. This super tiny number, 10 to the minus 36 kilograms, is just the limit that we have set on the mass of the neutrino. We don't even know it yet. But just to put that in context, the next lightest elementary particle that has mass is the electron, that has more than 500,000 times the mass of the neutrinos, at least, because we don't even know that yet. The other weird thing about the neutrinos is that they come in 3 flavors that we call electron, tau, and muon. This may sound weird because we use the word flavor in particle physics, but it's kind of a charge. Like we have positive charges and negative charges. These are 3 different types of charges. But the weird thing about neutrinos is that they change from one type of charge, one of these flavors, into another as they fly. They're all neutrino, but they can change from one property to the other as they propagate. I mean, this will be as weird as, I don't know, a bat, or not, let's say a bat, but an owl flying into an eagle, flying into a dove. I mean, they will always be birds, but they're oscillating in their type one from another as they fly. That's what neutrinos can do. And the thing that makes them so hard to detect is really that they only interact through what we call the weak force. And the probability of having one of these interactions is extremely small. And that's how 100 billion neutrinos can fly from the sun through each centimeter square of our bodies without us noticing it. Okay, so even with about 10 to the 15, sorry, that's 10 to the 15, not billion, but 10 to the 15 neutrinos going through our body over our entire lifetime, there's only a 50-50 chance that one of them, of these 10 to the 15 neutrinos, will interact with our body. So you can imagine how hard it is to catch them. And just to lead to the next topic, I will mention this. This is kind of a particle physics diagrams. I will only say here that whenever a neutrino interacts, there are some of these neutrino interactions that lead to the production of a charged particle. That's the only important thing about these interactions, because that will be important for the detection of these neutrinos. Okay, so how do we detect neutrinos? If we have a chance in 2 that all of those neutrinos that go through our body over a lifetime, let's say 70-something years, if you only have like a 50-50 chance that one of them will be interacting with our body, you can imagine that it will be very hard to wait a long time to detect enough neutrinos to do anything with them. So you really want a massive, massive object to put in front of the neutrinos so that you have that interaction probability be larger, because so rarely it happens. And here I'm showing you a picture of one of the biggest, let's say, human-built neutrino telescope. Is called a Super Kamikande detector. It's in Japan. It has a diameter of almost 40 meters and a height of also 40 meters. And what you see here on the walls are light sensors. And these white figures that you see in this platform, these are human beings. So you can imagine what the scale of this thing is. So as I said, whenever a neutrino interacts, sometimes it will produce charged particles, and these charged particles now become visible because they can interact through the electromagnetic force, which is much stronger than the weak force, as the name implies. These charged particles that are produced in these neutrino interactions travel faster than the speed of light in water, because at some point this whole detector will be filled with water. And when that happens, there's what we call the emission of a type of light that we call Cherenkov radiation or Cherenkov light. There's kind of a blue or UV light that's emitted on a cone. Okay, it's kind of similar to a sonic boom from a plane, but it happens with light instead of sound. And that particular cone has a very specific geometry that we can calculate based on the properties of water. So based on the lights that all of these sensors in the Japanese detector detect, and based on their on the shape of that cone, we can infer the direction, the energy, and other properties of the neutrinos. You may have seen sometimes chunk of light without knowing it. If you have seen a picture of a nuclear reactor that is operating, you will see some kind of bluish glow coming out of it, and that's actually a chunk of light being produced by charged particles in the reactor pool. So as I said, these light sensors that you see kind of covering the walls and the floor and the ceiling of this detector, they record this chunk of photons coming from not the neutrino itself, but the particles produced by the neutrino interaction, and you can infer out of that the direction of the neutrino. So in this case, for instance, for that particular detector, you have a cone produced by one of these charged particles that were produced in a neutrino interaction. And out of the, as I said, the shape of that cone, the size and the timing and the different different geometry of this detector, you can actually calculate where that neutrino was coming from. Okay, so that is about neutrinos, but as I said, these are neutrinos at lower energies in this kind of peak that we have. These are neutrinos about 1 million times the energy of visible light. But we actually want to go to much higher energies, and that is because that's where most of these extreme sources are that we want to study with neutrinos. Things like active galactic nuclei that are powered by supermassive black holes, things like accelerators of particles that reach energies that we cannot reach at Earth, things like chaotic catastrophic events like a gamma ray burst that lead to the either the explosion of the massive star or the merger of neutron stars. All of these things may emit neutrinos, but at much higher energies. And that is a very big challenge for neutrino astronomy, because if it was hard to detect neutrinos at lower energies where you have so many of them, like in this plot I'm showing here, kind of the flux of neutrinos is how many neutrinos we detect per unit time at Earth. And you see that on the y-axis, this very large range of numbers from 10 to the 13 to the 10 to the minus 36 means that there are many more solar neutrinos than there are AGN neutrinos, for instance, or that we expect them to be. So kind of a benchmark astrophysical flux for these high energy neutrinos above 10 to the 12 electron volts, so about 1 trillion times that of the energy of visible light, is about 100,000 neutrinos per square kilometer per year. So that's not much, actually. In order to detect this neutrino flux, you need a gigantic detector, something that has a mass of about 1 gigaton, so or 1 billion tons of something. And in order to get that, you need about a kilometer cube of water. And if it was hard and expensive to build this detector in Japan, you can imagine how big and expensive it would be to build a cubic kilometer of anything. So it came to the, and one of the reasons, sorry, why we want to actually build those detectors, not only to study these different objects that are out there, like AGN and so on, but also to determine the origin of what we know to be the highest energy particles in the universe that we call cosmic rays. In this case, in the case of cosmic rays, they're charged particles. So as I said before, they don't point back to their source. So really, by figuring out if there are neutrinos coming from the same direction, we can understand the origin of these cosmic rays, of these charged particles. We've known about them for over a century. We haven't determined what the origin is, but we can find them using neutrinos and also gamma rays, because every time there's a cosmic ray that interacts with something on the way to Earth, that interaction will lead to neutrinos and photons being produced at the same time, gamma rays and neutrinos. So both of those particles are neutral, so they travel in straight lines. And if you happen to see in the sky a joint source of both neutrinos and gamma rays, you have a very good guess that that could be a source of cosmic rays. Okay, so now that we have the motivation why we want to build it, how do we actually build a neutrino telescope that has a size of about 1 kilometer cube? And that goes back to essentially the 60s, where Markov and Zelensky were working on an idea for how to build such a detector, and they proposed to do it on a natural body of water. Okay, instead of building a gigantic pool that has a size of 1 kilometer cube, which will be extremely expensive to build, you can actually use a very deep lake or ice and then put detectors there, so you can actually see that light, the chunk of light produced by the interaction of the neutrinos. So as I said, large target masses can be found in natural bodies of water, and that was proposed already in the 1960s. So these high energy neutrino telescopes, the one that are aimed to detect neutrinos from AGN, GRBs, and so on, use this principle. Instead of having kind of a container, a cylinder with walls made of or surrounded by light sensors, the sensors are kind of in a volumetric array. So they're kind of a three-dimensional sensor. So every time you have a neutrino interact, it will produce a charged particle, for instance, a muon, like you can see here. That muon will travel through this three-dimensional array of light sensors, producing chunk of light. And out of that light, you can actually figure out where that muon was coming from, and therefore infer where the neutrino was coming from. Okay, so we need just a large body of water or ice that can be instrumented with the sensitive light sensors. And the good thing is that muons can travel actually for very long distances, from something between 50 meters to over 50 kilometers, depending on their energy. So even neutrinos that interact far away from our sensors, they can still reach the detector and provide a much larger volume with which to detect them. So the main options for deploying these neutrino detectors are really deep glacial ice, or lakes, deep lakes, or the deep sea. So the current generation of telescopes actually uses this principle. We have three. One of them actually was deactivated very soon, very recently. There's one called Baikal GVD. It's one in the deepest lake in the world, Lake Baikal in Russia. It has already reached about a third of the kilometer cube that is needed to build a working neutrino telescope that is supposed to see these things. And until very recently, we actually have one in the Mediterranean Sea called Antares, but it's very, very small. It's about a 1/100th of a kilometer cube. And finally, I want to talk more about IceCube, because IceCube is the one, first of all, is the one I'm involved with, but also is the first one to reach 1 kilometer cube in size, which is the target mass that you need to do neutrino astronomy with. It's composed of more than 5,000 sensors deployed over, as I said, 1 kilometer cube of ice at the South Pole, and the construction finished in 2010. So this is the one I'm going to be talking about more. It's not only the one that is fully built and operational, but also the most sensitive one. So this is the South Pole, and you cannot see the neutrino telescope anywhere here, because actually the neutrino telescope is buried in the glacier at the South Pole. And the good thing about the deep Antarctic ice is that it's very abundant. There is everywhere ice, and hope we can keep that ice for a long time. It's very transparent. We cannot even make ice in the lab that is so transparent as the deep ice at the South Pole, and it's very dark. So the light that you see in the deep ice at the South Pole is mostly coming from these cosmic particles, which is pretty amazing. So this is the IceCube Neutrino Telescope. You have here our webpage if you want to visit it. And as I said before, it's composed of more than 5,000 of these sensors that have a kind of a glass pressure sphere, so the ice doesn't get into the light sensor. And here on top, you have this little building that you may see in this picture here. And that is where we house the computers. All this information coming from these light sensors goes up to the surface via these cables, and then travels to the computers that are housed there in this little building. So as I said, it's the first kilometer cube neutrino telescope, more than 5,000 sensors deployed at depths between 1.5 and 2.5 kilometers. So really the top part of IceCube starts almost a mile deep into the ice, and it goes all the way up to almost 3 kilometers in depth. Its construction, as I said, finished in December of 2010, and it has other components that are dedicated to other studies of cosmic rays, actually, and lower energy neutrinos. So the construction started in the summer of the austral summer, the southern summer of 2004-2005, with the deployment of one of these long strings of sensors that each one of them has 60 sensors attached to it. And then, because this is working at the South Pole, you can only build during the summer there, which is still very, very cold. So over the next seasons, IceCube started growing and growing. And while it was growing, it was actually taking data. So here started with one string, one cable filled with sensors, then upgraded to 9 strings, 22 strings, 40 strings, 59, 79, and finally 86 strings, which was the completion of the full detector in December of 2010. So this is how it looks when you're deploying the sensors. This hole goes, as I said, almost 2.5 kilometers deep into the ice. At some point, it actually reaches water. And what you see here is the cable that brings the data from these light sensors to the surface, and one of the sensors we can see here illuminated. So how do you actually build such a big detector in the ice. I mean, you have to drill some holes into the ice to deploy these long cables. And you will think that it is very complicated, but I mean, it's pretty straightforward. Of course, it's very expensive to build it, but still it's a very straightforward idea. You just put a long hose with hot water and you just point it down, and the hose will just drill a hole through the ice. You first kind of try to melt the top part, which is mostly compacted snow. You take that out, and then you replace that serpentine with this long hose with high pressure water that drills all the way down to 2.5 or almost between 2.5 and almost 3 kilometers deep. Once you have done that, you have to do this very quickly because the water will freeze again in place. You take out that hose and you put in your cable with light sensors. And once you've done that, the sensors will be frozen in place essentially forever, hopefully forever. So once you've done that 86 times, you have yourself a nice neutrino telescope. And this is kind of some pictures of how the drilling stations looked at the South Pole at the time, and kind of the deployment of the cables that bring the data from the sensors to the computer center that we have there, the IceCube lab. So this is in the end IceCube. This is how it's been built. And as I said, these are the depths at which these things are located. These sensors are located. So how does IceCube see neutrinos? So as I said, we don't see the neutrinos directly. We see the light, the chunk of light produced by charged particles that are produced in the interaction of the neutrinos. So we typically have two different types of event topologies or shapes of events that are produced by neutrino interactions. The first one is this one, the muon track. So you see here that it's kind of an elongated shape, and that each one of these dots is one detector of those strings that saw a little bit of light. Okay, the size of each one of these dots indicates how much light it was seen, and the color indicates the time. Red means early and blue means late. That means that there was a charged particle, a muon in this case, that entered the detector through the left here and emerged kind of somewhere up and to the right towards the blue end of that elongated shape. And since you have that kind of elongated shape, you can actually reconstruct where that neutrino and where the muon was coming from in the sky. And that's the kind of the most important thing to do astronomy. You want to reconstruct where the neutrinos are coming from in the sky so you can put them in a sky map and figure out what's there. You also have other types of neutrinos that through their interaction could produce what we call cascades. That are mostly almost spherical shape, and you can see that this is not particularly pointing in any particular direction, but if you apply advanced reconstructions to these kind of events, you can still get almost 15 degrees angular resolution. I mean, to do astronomy, this is terrible, as you can imagine. We're used to arc seconds or even less than arc seconds with Hubble and with ground-based telescopes, and we're thinking that for us, for neutrino telescopes, let's say a 0.1 degree angular resolution is fantastic. If you go outside on a moon on a night when the moon is up, the size of the moon is about half a degree. So that's about our angular resolution, and that is the good angular resolution for a neutrino telescope. The fact that you can see in the face of the moon, you can see little patches of dark stuff, that means that your eyes have better angular resolution to the sky than IceCube does in neutrinos. Of course, you can see only light and IceCube sees neutrinos, but still, we're working hard to improve this angular resolution because it's one of the key ingredients in doing astronomy. So here, let me show you kind of a candidate neutrino event. This was an actual recorded event. And what you'll see here is kind of a reconstruction. This line that you see coming from the top left is the reconstructed direction of the neutrino. And as it enters the telescope, you'll see that it leaves traces of light behind. The blue bubble there is also kind of an animation showing where the chunk of light was produced. But in general, you see that kind of that elongated shape again, and therefore that allows us to reconstruct where that neutrino was coming from originally. Okay, so what do we need to do neutrino astronomy? First, we need to find cosmic neutrinos, and as we will show you, it's not that easy. And then we need many of these cosmic neutrinos because you want plenty of them so that you can put them on the map and figure out where they're coming from. That means that since we don't have a control over how many neutrinos the sources can produce, the only thing we can do is make bigger and bigger telescopes that can give us more and more neutrinos. The other thing is that we need good angular resolution, and we also want energy resolution for the energies of these neutrinos. I won't talk too much about it, so I want to concentrate just on good angular resolution. And we also want to do these measurements in low backgrounds, which means that we can separate the neutrinos that are actually there from everything else that looks like a neutrino, but it's not really a neutrino. Okay, so why is it so hard to find these astrophysical neutrinos that are produced somewhere in the universe? It's because we do that search on a background dominated on a background dominated case. We have, let's say, IceCube is at the South Pole, so I've flipped around the globe. I mean, as a Southern Hemispherian myself, this is how I view the world anyway. So you have IceCube here, of course, not to scale. We'll wish to have IceCube be as big as a good chunk of the Earth, but most of the events, most of the things that IceCube sees continuously at the South Pole are actually produced by cosmic rays that hit the atmosphere and produce these muons. These muons are not being produced by neutrinos, they're just produced by cosmic rays that interact with the atmosphere, but they look a lot like a neutrino. There are still muons going through our detector, and there's also the signature of neutrino detections. Okay, so that's downgoing muons that can travel through your detector. Then the other thing is that since neutrinos can go through everything, they can also go through our planet. So even neutrinos coming from also cosmic ray interactions, but on the other side of the planet can still reach IceCube and pretend to be an astrophysical neutrino. So we want to remove both the cosmic rays, cosmic ray muons that that pass as a neutrino, and also the atmospheric neutrinos that are also produced by cosmic rays, but are not really produced by direct astrophysical sources. And finally, we have every now and then we'll have an astrophysical neutrinos coming directly from one of the sources that we want to study. So what is the challenge here? How big is that challenge? We detect about 3,000 muons per second in IceCube. And we detect about 100 atmospheric neutrinos per day. None of those things are the main ones that we want to study to do astronomy with neutrinos. We want to get rid of them. But we only detect about 1 neutrino per month that we think is astrophysical in origin. That means that we have to, for every astrophysical neutrino that we have in our data, we have to throw away about 10 billion things that look exactly like a neutrino. So it's a very challenging thing to do, okay? But the first indication that we actually have astrophysical neutrinos in our data came in 2013 when we identified these 2 events that were named Ernie and Bert, as you can obviously see. I mean, they exactly resemble the Muppets that are associated with them. Not really, but still. How do we know, or why do we think that these are astrophysical neutrinos? Is because they have a very high energy of about 1 PeV, 10 to the 15 electron volts, which also means 10 to the 15 times, about 1,000 trillion times the energy of visible light. So we're way out there, things that will be very hard to see with gamma rays, almost impossible to see from very far sources. So why do we think that these are astrophysical? Is because these atmospheric neutrinos that are produced in cosmic ray interactions in the Earth only reach to so high energies. They don't go that far in terms of energy. So if you see a very high energy neutrino, that is likely to be astrophysical in origin because the cosmic rays hitting our atmosphere cannot create that. Okay, so that was the first evidence that we have astrophysical neutrinos in our data. Since this was found, there was a question immediately, are there more in data that we haven't seen? So how can we find neutrinos in our data, throwing away everything else that looks like a neutrino? So this is how a veto works, and this is how this detection happened. Let's say that you have a muon. A muon is producing shrink of light, as I mentioned before, and as it travels through the IceCube detector, it's always emitting light. Okay, so we define kind of a boundary around our detector made of other parts of the detector. So the detector itself, we define parts of the detector to be what we call a veto. So if anything that goes through our detector also deposits light in the veto region, we throw that away because we think that that is a muon that came from above or from below even, but that is most likely produced by just a muon and not a neutrino. Now, neutrinos can go through everything, and they can also interact within our own detector, sneaking in through the veto and producing a frequency interaction within our veto. And that's how we actually selected for these neutrinos, because these neutrinos will come in and they will first interact in the ice, and then you'll see a muon suddenly appearing in the middle of your detector. And the only way that you can explain that is actually if a neutrino came there. So now you can identify neutrinos. You can throw away all the muons. And now if you require that the neutrinos have enough high energy to kind of remove the atmospheric neutrinos, you can be pretty sure that you're talking about astrophysical neutrinos. So this is what it looked like. You have all these red points. I mean, this is kind of complicated axis. You have three-dimensional axis. You have how many events you detect along the z-axis, the total charge of the event, which is an indicator of the energy of the event in kind of the x-axis, and along the y-axis you have how much light they deposited in the veto region. And you can see that, I mean, it's kind of hard to see, but if you follow kind of this evolution of this kind of three-dimensional surface, you see that the three-dimensional surface has a pretty stable shape all the way up to here, where you have many high energy events that have a high energy because they saw a lot of light in the detector, and also they don't produce any light in the veto region, meaning that those are neutrinos, and those are actual astrophysical neutrino events. So that was the first detection by IceCube of astrophysical neutrinos at very high energies, the ones that we're interested in. So that's the first ingredient to try to do neutrino astronomy. Okay, so ever since then, in 2013, we have been collecting additional evidence for neutrino astrophysical neutrino observations, and we have a very solid detection of just the neutrinos themselves. That's the first ingredient in trying to do astronomy, just figuring out that there are astrophysical neutrinos out there that we can use to do astronomy. And since then, as I said, we've been building up on this evidence for astrophysical neutrinos that we have a strong detection of right now. So where are they coming from? That's the next question that you may ask. If you plot the neutrinos, these are not sources yet. These are individual neutrinos that you can plot in the sky. This is what the galactic sky looks like in neutrinos. In this kind of representation, the galactic plane, the Milky Way, is kind of flat along this horizontal line. And each one of these little dots is not a source of neutrinos, but it's a single neutrino that came from that direction. And since IceCube can detect neutrinos and neutrinos can go through everything, you can see both neutrinos coming from above IceCube and also neutrinos going through the Earth and into IceCube. Well, at some point, the neutrinos are so high in energy that actually some of them are absorbed on the Earth. But you can see here that we have plenty of neutrinos across the entire sky. At the level of about, as I said, 1 per month. So we collect about a few tens or so a year. You can see, at least from just taking a first look at this, how these neutrino events are distributed, that none of them, or there's no clear indication that most of them are just distributed along the galactic plane. They seem to be kind of distributed both above and beyond the galactic plane. And that tends to favor that most of them will be coming from sources beyond our own galaxy, meaning that they're in extragalactic space. So that perhaps the contribution of our own galaxy to the neutrino sky is not so high compared to the neutrinos that we have detected so far. So, okay, now we have this sample of neutrinos. Let's look at lower energy neutrinos as well to see if we see any evidence for neutrino sources, right? Any kind of particular point in the sky that's emitting more neutrinos. And as I said before, we have detected neutrinos from across the sky, going through the Earth and from above. And if you put them on a sky map for 1 year of data, this is what it looks like. And it looks pretty even, right? That's because most of that sky map is made of background events that are not really astrophysical neutrinos. And there's no obvious indication that any of these little patches of neutrinos or clusters that you see are more significant than others. So in taking the first years of data, we didn't see any strong indications of neutrino sources. Most of these neutrinos, therefore, most likely are from background events. So we search for self-clusterings of these neutrinos to look for an excess that could not be produced by just random alignment of background events, but could be a point source of neutrinos. And in order to find the sources, we have taken kind of some pointers from everything else that is out there. As I mentioned before, if we detect gamma rays and neutrinos coming from the same point in the sky, we know that that's a good indication that that could be a cosmic ray source. So why not use the gamma rays to tell us where to look for neutrino sources? If you look at the gamma ray sky, taking here this picture across the entire sky by the Fermi satellites that I mentioned before, the glow that you see here is the Milky Way in gamma rays, and each dots that you see here at high galactic latitudes, these are not stars, these are supermassive black holes at the center of these objects that we call active galactic nuclei. Okay, so we can take each one of these two ingredients, we can take galactic sources, things that are in our own galaxy like supernova remnants, pulsar with nebulae, and look for neutrinos specifically in that direction so that we don't waste time just looking around at the entire sky. Or we can also look for neutrinos coming from each one of these AGN that we're going to explore more in the coming slides. So I will go through a bunch of disappointing slides. We have looked so far at neutrinos from the galaxy, and just based on the most recent observations, we don't see a strong evidence for emission from the galaxy itself. So from this kind of band of gamma ray light, there's no strong evidence, but we're fine-tuning our analysis to improve our sensitivity to these neutrinos. And perhaps in the near future, we may be able to see that that emission, because we're getting very close to what the models predict should be the flux level for the neutrinos coming from our own galaxy. Okay, so so far there's no significant correlations with the galactic plane, but as I said before, our sensitivity is improving as we take more data, and therefore at some point in some day we may start seeing neutrinos from our own galaxy. We also look in the direction of these active galactic nuclei, and again, in that case, we don't see a strong evidence, with strong correlation between the gamma ray blazars, gamma ray active galactic nuclei seen by Fermi, and the neutrinos detected by IceCube. And again, in that case, we have said, okay, we expected perhaps some neutrinos, but we haven't seen any strong evidence for that yet. And the other kind of very popular source that was out there, this gamma ray bursts that are either produced by the collapse of a massive star or the compact binary merger, let's say, of two neutron stars. They have been promising neutrino sources for a long time, and we looked in the direction of those GRBs to look for neutrino emission, and again, we haven't seen any correlation. Okay, so how do we actually know that we're pointing our telescope in the right direction? Our telescope is just a block of ice that has a 1 km cube, right? So how do we can we tell if we have not seen any single source that our telescope is telling us that neutrinos are coming from the place where we claim they are? Well, it happens that some of these cosmic rays, beyond being a pest and we try to remove them to search for neutrino sources, they're actually very useful, because cosmic rays come from all around us, bombard the Earth from all directions. But there's one particular direction in which cosmic rays tend to be coming less from. I mean, there are less cosmic rays coming from that direction. And that's the direction of the moon and the sun. As you probably know from solar eclipses and lunar eclipses, from solar eclipses, the moon and the sun have the same angular size in the sky, half a degree. So if cosmic rays are coming from the deep sky, the space, from the outer space somewhere in the universe, and are getting to Earth, the ones that should be coming from the direction of the moon or the sun will be actually blocked by the moon. And that's what we call the moon shadow in cosmic rays. So there should be less cosmic rays hitting IceCube from the direction of the moon than there would be otherwise. So by looking at that particular shadow effect, we can actually see the shadow. I mean, these are how many events we see from the direction, how many cosmic ray events we see from the direction of the moon. And you see that right at the location of the moon, we see a strong deficit from what you would expect otherwise. And using that, we can actually calibrate our pointing, because if you see that shadow, it means that we know where these muons are pointing in the sky, and therefore we know where the neutrinos are coming from. And other telescopes like Antares have done the same thing. So using the moon shadow in cosmic rays, we can actually calibrate our telescopes. And we know that our angular resolution at the moment is about 0.5 degrees, improving to higher energies, but 0.5 degrees. And in terms of absolute pointing, it's less than 0.1 degrees. So pretty good angular pointing for neutrino telescopes. Okay, so since we started saying that neutrinos have very high energies and are likely astrophysical in origin, and we detect about one a month, we can actually use this information, because if we know that there is a neutrino in the sky at a particular time, we may not see perhaps many more astrophysical neutrinos coming from that same point in the sky very shortly. But what we can do is tell the astronomical community, please point your telescopes in that direction, because that means that there could be something going on there at that location that is emitting neutrinos, and perhaps it is flaring also in gamma rays, in X-rays, and so on. So in IceCube, we started this real-time alert system in 2016. You can actually subscribe to it yourself and get neutrino alerts every time IceCube detects a neutrino that is likely of astrophysical origin. And as I said before, this is the sky as seen from the South Pole. The southern sky is on the bottom. The northern sky that you see through the Earth only is on the top. And I'll show you a little video of the start of this real-time program between 2016 and the late part of 2017. So these are the neutrinos that are coming, and you see kind of the dates at which they come and where they came from in the sky. And I stopped there because there's one particular neutrino event that was very interesting. It's called this I-170922, and that is because the date that it was detected was September 22nd. This is a typo here, of 2017. And this was this neutrino. The muon that was produced by this neutrino traveled through our detector, and it produced a pretty nice track of light, and we're able to reconstruct the direction of that neutrino back into the sky. And lo and behold, if you look back at the sky at that particular location, there's an active galactic nucleus that at the time of the observation of the neutrino was strongly flaring in gamma rays and in X-rays, and it was showing activity throughout the electromagnetic spectrum. So as I said before, an indication that there are gamma rays at the same time as neutrino emission, it's a good indicator that that could be a cosmic ray source. So this was super exciting because this was the first time we had seen kind of a coincidence between one of these neutrinos we had detected and one of these sources, and that the source at the time happened to be flaring strongly in gamma rays and X-rays. So just to mention very briefly what are active galactic nuclei, they're the most powerful persistent sources of electromagnetic radiation in the universe. They are powered by the supermassive black hole and the matter that falls into that. And many of them display, or at least a fraction of them display, these relativistic jets. And when these jets are pointed at us, we call them blazars because they're shining kind of this beam of radiation towards us. And we want to study them at the highest attainable energies. And of course, gamma rays and neutrinos are a specific way to do that. In the detection of 170922, this IceCube neutrino event, we notified, as I said, the astronomical community, and these were all the telescopes, both on the ground and in space, that participated in the follow-up of that campaign. And with the data collected from those observations, we were able to put together this picture of the gamma ray blazar. In this picture, you see energy as in the x-axis and just the number of photons that you're seeing. These are just electromagnetic observations. So this is along the y-axis, this amount of energy in at that particular energy range that you can detect from that source. And here, the high energy emission is the one that's most interesting because it's the one that probably is connected to the neutrino emission. So that was the first chance correlation evidence for neutrino source that we have detected. And that is the evidence for the connection between this particular neutrino event and this blazar that we detected called TXS 0506/056. Because IceCube has been operational since 2010, now that we have identified a source that is of particular interest, we can look back at the data because the IceCube doesn't point in any particular direction. It's always surveying the entire sky. So doing that, we actually found an excess of neutrinos coming from the direction of that source that dated back to 2014 and 2015. And luckily, no electromagnetic telescopes were pointed at the source at the time, only wide field instruments that have limited resolution and sensitivity. But we found additional evidence that there was something going on in that part of the sky. So this is perhaps the first evidence that we have of neutrino sources appearing in the sky. More recent alerts, I'm going to show you what happened after that. So you can see that about once a month, we have a neutrino alert coming from IceCube that says, hey, look at that location in the sky because there could be an astrophysical neutrino coming from it. And this will keep going. I think I made this video all the way up to about 2021. And if you want to see them with your own eyes and actually get kind of a nice view of the IceCube detector, some of our colleagues in IceCube had developed this app for your phone where you can see a virtual reality representation of IceCube. You can get it downloaded from the Play Store or the iOS App Store. Just look for IceCube AR, and you can actually see some of these neutrino events, and it will notify you it will notify you when you have a new alert coming from IceCube. So it takes on average, it only takes 30 seconds for an alert for a neutrino to be detected at the South Pole and you getting that notification. So it's pretty amazing how quickly things travel from the South Pole all the way to your phone using this technology. And actually, we had one earlier today. Today morning, I was busy sending out some information about this alert. This is one neutrino event that went through our detector like this. And beyond the ones that we detect often, there have been several additional claims for correlation since the correlation between this particular event in 2017 and this blazer called the XSC of 506. So we may be seeing kind of the tip of the iceberg in terms of trying to find the sources of these neutrinos. Beyond just looking for particular correlations between individual neutrino events and just sources that we know are out there that could be gamma ray sources or X-ray sources, we're also looking for, just as I said before, clustering of neutrino events in the sky. Just neutrinos, if there are many neutrinos coming from the same point in the sky, that is unlikely to be produced by just background, by just chance, it's possible that that's a neutrino source. And in the recent analysis of 10 years of IceCube data, we have found an excess. Again, this is evidence for something. Evidence in the particle physics lingo means that the probability that this is something that happened just by chance is about 1 in 370. So it's not a very small probability. I mean, it's not a very large probability, but still, it could be by chance that this happens. So we're still refining our data analysis, and we're looking more at this data. We're collecting more information. So perhaps if this keeps increasing, we will get to an actual detection of this source at some point in the future. We cannot say yet with the data that we have in the 10 years of so far. Okay, so this particular source is very interesting. It's called NGC 1068. It has a beautiful picture. Unfortunately, it's not taking neutrinos. It's taking an optical light. And what we think is that at the center of that source, if that can be, a way to explain these neutrinos coming from that source is that the black hole at the center of that galaxy has, as many of these black holes have, they have an accretion disk, and they have this region called the corona, and that is producing many photons, and these cosmic rays that are being accelerated near the black hole interact with those photons, and they produce neutrinos and lower energy radiation, mostly in the X-rays. So there are some theories out there of how you could be producing neutrinos to try to explain this observation, this evidence for neutrinos coming from IceCube. Okay, so as I said, the future is just to get more neutrinos coming from the sky. As I said, the ingredients to Neutrino Astronomy is that we want first to have a cosmic flux of neutrinos. We have that already. We're improving our angle resolution. We're taking more data. IceCube is taking data 24/7, so nothing stops it. It looks at the entire sky at once, so there's no issue there. The thing is that IceCube has a limited size, so we're limited in our sensitivity by just the size of IceCube. So in the next decade, the idea is that more telescopes will be deployed, and also IceCube itself will be expanded to look more deeply into the neutrino sky. As I said before, this effort in Russia to build to keep expanding this Baikal GVD detector. This was the status as of last year. Right now, of course, things are uncertain, let's say like that, and therefore I don't know exactly what the status is of Baikal GVD. But there's also a large effort to put a neutrino telescope at the bottom of the Mediterranean Sea. That's called KM3NET. That's mostly led by European institutions. And the idea is that that telescope will get to the volume that IceCube has right now in the next few years. So what are the plans for IceCube? The idea for IceCube is that we want to build a second generation of IceCube Gen 2, which will be an expansion of the current IceCube. It can be something between 6 and 10 times the volume of IceCube, so a much larger detector that gives us better sensitivity, better angle resolution. And therefore, over the coming years, there will be a lot of research and development that has to go into the detector part of it. So there will be new strings being deployed into the ice at the South Pole, hopefully if the pandemic delays don't keep pushing this back. But the idea is to push kind of our sensitivity limits in terms of how sensitive we are to the neutrinos that are coming from outer space. And the Gen 2 construction is likely to continue until the 2030s, early 2030s. But of course, IceCube being modular, it can take data while it's being built. So it's not like we'll have to wait until the 2030s to see something. Each time we put a new string with light sensors into the ice, we see our detector improve in size and therefore in sensitivity, and we can get a better look at the sky with an ever-increasing detector. So in summary, I hope that even though I wasn't able to show you pretty pictures taken with neutrino, other than perhaps the sun, like the ones that Hubble takes and the ones that we're starting to get some flavor of from JWST. I think it's equally as exciting that we're seeing the birth of a new type of astronomy that's done with neutrinos. So in this case, we first detected this flux of astrophysical neutrinos. We may be seeing the first evidence for, or we're seeing the first evidence for sources out there, and we'll keep improving our data reconstruction and also keep taking the data. So most likely we'll start to see more and more sources in the coming years. Another thing that will be important, as I said before, is that whenever we notify the community that there are telescopes out there that can point back at the sky from the location where these neutrinos were, so that we can also understand more about these neutrinos. So we combined photons with neutrinos to do this kind of what we call multi-messenger approach to study the sources. And as I said, also, there are more neutrinos coming online in the coming decade, so please stay tuned. And to close, I want to thank again STSI for hosting me. This is a scan that my mother sent me from kind of a book or notebook that I used when I was 10 years old. And as a kid, I was always very excited about JWST, about Hubble, and I kept notes of where STSI was in Baltimore, and you can see kind of my drawing of what I thought STSI looked like at the time. So, I mean, it's a privilege for me to be part of this public series, because in a way, I'm a product of this, the public efforts of STSI, of inspiring next generation of physicists, and therefore, I want to thank my host again for having me, and you for being in this talk. So thank you.
Thank you, Marcos. I think I'm going to have to share that picture that you just shared at the end of your talk. I'm actually going to see a kindergarten class tomorrow, so maybe I might steal that. So that's great talk. Some amazing things that I learned in the talk as well. And so let me start off with some of the comments that I'm looking at in the YouTube chat here. People are very, very interested in what you just described in terms of neutrino and particle physics here. Thank you for the clear simplicity of your explanations of this very complex field. It is deeply appreciated. Absolutely incredible work. So kudos to you in explaining how we can study the universe using these particles. So I do have a quick question for you.
Sure.
Have you ever been to the South Pole to help support IceCube?
Not yet. I would love to. I mean, I think that I had a chance in 2011 when I was a grad student still, but I also had a baby girl on the way. So I think that was the first priority. When you go to the South Pole, you have to stay there to go in and out for about a month. In the winter in Wisconsin. I mean, that was a pretty bad time to leave my wife with a baby on the way. But hopefully, if the pandemic kind of restrictions are relaxed, of course, that this is being a very remote environment, is hard to it's very problematic to introduce a disease into the South Pole Station. So there are many precautions that are taken just to prevent that. And one of them is that the number of people that can travel has to be limited to the extreme. So just the kind of the people necessary to keep the station working and the detectors working. But hopefully with the construction of Gen 2, there will be an uptick in the number of people, and hopefully I'll get to join soon.
That's great. Yeah, I think it's a very unique location, and only so many people have been to the actual South Pole.
That's right.
And I can say my husband has not been to the South Pole, but he has been into Antarctica.
Oh,
so
wow.
To support, this is long ago, but that's okay. So I will start off with a question here that was posed in the YouTube channel. So in the beginning of talk, you showed the electromagnetic spectrum from microwaves all the way down to gamma rays. So one of the question from the audience is, why is the gamma ray section so big on that graph? And are there subdivisions? Like, do they have names? Like, for example, yes. I can say, you know, infrared, we talk about the near infrared and the mid infrared, far infrared. Is there something similar for gamma rays?
That's right. I can go back to the slide if that helps. I will have to go by a little bit, and then yes, there are divisions in that very wide span of, you will think that visible light, when we think about, oh, this is so different between infrared, and as you know, I mean, Hubble and GWST are very different telescopes because they're going to be targeting different parts of the electromagnetic spectrum. But when you look at how narrow those bands are, the visible UV to the IR, and you compare it to how wide gamma rays are, is because anything that goes above, let's say, a few hundred thousands of the times the energy of visible light, that is considered a gamma ray, no matter if your energy is 100,000 or 10 to the 20 electron volts. So you're always a gamma ray. The same thing applies to radio. Below a certain energy, you're always radio, no matter if your wavelength is a meter or the size of the universe. You're always in the radio band. But we have some bands. We have the ones that can be detected mostly from outer space, between a few hundred thousand times the energy of visible light, so a few hundred keV, to about a few MeV, a few million times the mass of the energy of visible light. That is what we call high energy gamma rays, up to about GeV, or a billion times the energy. And above 100 GeV, we have very few photons coming from outer space. And actually, that's the other thing that I do, that I work with IceCube, but also work on gamma ray instruments. The satellites are too small to detect gamma rays above 100 GeV on a steady basis. You need something much bigger that has not a size of a satellite, which is a couple of meters squared at most, if you can fit it in a rocket. You need hundreds of thousands square meters, and it's very hard to launch something as big. But luckily, we can do that from the ground. And actually, there are these telescopes, the one I work with, that's why I include it in a very biased way, called Veritas, at the long end of that electromagnetic spectrum, that is actually looking for gamma rays above 100 billion times the energy of visible light from the ground, actually from Arizona, south of Tucson. So about 20 kilometers away from the Mexican-US border, there is Veritas, and there are two other telescopes of this type that detect gamma rays at those energies.
Great, thank you, Marcus. I have one other question, and then Grant, I think you can join us right after that question. So if you go back to that electromagnetic spectrum graph, Marcus. Mm-hmm. So you have that some of the high energy gamma rays are absorbed at various energies to various distances. So in specifically, I'm curious to know what is doing the absorbing towards close by in our galactic center for some of those high energy gamma rays. What's the absorber to make them not be visible or detectable?
So there's a remnant light that permeates the entire universe, that was emitted by the first generations of stars, that today we call the extragalactic background light. It's very hard to measure, but we can actually do it with gamma rays. And this permeates everything from, I mean, since it's everywhere in the universe, it's around us right now, and it's also far into the reaches of the universe. So this is mostly infrared light as we see it today. It was not originally infrared when it was emitted, but it's mostly infrared light. And on top of that, we have the cosmic microwave background. So the frequencies of light that affect the gamma rays depend on the energies of the gamma rays we're thinking about. Most of the lower energy gamma rays at the end here of the spectrum, this blue kind of void that you see here, those are affected by that first generation of stars light, the EBL. And most at the higher energy end, they are coming from the cosmic microwave background, but they affect all light across the entire universe. The thing is that at this particular energy that I'm showing here, 10 to the 15 electron volts, we cannot even see into the galactic center, because on top of that light, there's also starlight from the galaxy itself. Just as the starlight from the galaxy also acts as a target. And these gamma rays actually interacts with light to produce charged particles, and therefore the light is absorbed and they never reach us. So we can only see, for instance, for that energy, we can only see all the way up to our galaxy at about 10 to the 15 electron volts. And we can see further into the universe as we go to lower energy gamma rays.
Great, thank you. So maybe at this point you can stop screen sharing, and We'll have Grant come on, and he will start. Grant, if you'd like to start asking some of the questions that we're seeing in the chat here.
Absolutely. Once I unmute myself. All right, so we've actually had a pretty engaged audience. So Marcos, thank you. This has been some good discussion going on. All right, so I'll start off with this one because this one is interesting to me as well. So, do you have any inkling as to the neutrino masses, like relative masses? AC in the comments says that different masses could affect the rates of oscillation, and his supposition is tau greater than mu.
So that's a very deep particle physics question. That is a big problem in physics. It's not just that so just to rewind and put things in context, we know of 3 what we call lepton particles, the electron being the most popular one that we know is in our atoms, in our body, but there are also a little bit more massive cousins to the electron that are the muon that I mentioned before, and also the tau particle. And they have different masses. The electron has about a mass of about half an MeV, and the muon has about a mass of about 100 MeV, and the tau is even more massive. What I want to say there is that the flavors of these 3 particles, electron, muon, and tau, are tied to the specific masses of the particles themselves. But neutrinos, they also have electron, muon, tau, but the masses are different and they oscillate with respect to each other. And the question of which one comes up, which one is the higher mass and which one is the lower mass, is a very complicated one because you don't have tau, electron, and muon. You have different neutrinos making different parts of it because they oscillate with each other. So there's a question in physics about, you can only measure kind of the differences between the different masses. This is kind of going into a tangent, but you can only measure the difference between the masses squared. So you don't know the sign of those differences. So we can have, for instance, the neutrino that has the most tau, and then the muon, and then the electron, order in that way, like it's happening with the charged versions of the particles. Or we can have what is called an inverted hierarchy, where we have one of them being much heavier and the other ones at the bottom. So actually, I don't have a good intuition for that. If I had to bet, I mean, unfortunately, there's one solution that will be very easy to measure if it's normal hierarchy or inverted, and the other one, it will take a long time to measure. But I don't have a horse on that race, unfortunately. I know that a lot of my neutrino colleagues do.
It's a lot more information than I started with, so I appreciate it. I like to ask those because I come in as a non-astronomer as well, so I try to pick out the stuff that I have no idea. All right, so let's see. Oh, there were quite a few questions about IceCube. One of them being, do you have any idea as to the time frame as to when IceCube will become available and start doing more science, as you were talking about earlier?
So if this is about, I mean, IceCube is operating right now, and in terms of making that data available to the public, for instance, or the physics or astronomy community, we have data releases that we sent out. Very recently, we released 10 years of data. This is essentially the entire data set of IceCube. It's out there for you to download. If you go to icecube.wis.edu, you can download 10 years worth of neutrino observations and try to see if you can find a source. We have been looking through this data, but there could be out there people that think that perhaps it's not AGN, for instance. There could be some other weird type of source, and therefore, if you look at those specific points in the sky, if there are more neutrinos coming from that direction that you would expect from just chance, then you have a solid detection of a neutrino source. So that data is there available. And in terms of just the continuation of IceCube, we keep taking data all the time. As I mentioned, we just saw an alert this morning. Luckily, I'm still very jet lagged from the trip to Paris, so I was still awake when it happened, so I could respond quickly. But beyond that, we will keep taking data until the construction of Gen 2. And IceCube itself, let's say the current generation IceCube, will become a part of Gen 2 because it will be just a larger volume surrounding the existing IceCube. So as the detector expands, we won't stop taking data. We'll just keep going and improve the sensitivity of the telescope.
I think that's more what they were asking. Yeah,
Okay.
Thank you. Okay, so moving forward as well, again, IceCube, how long do you expect the sensors to last?
They're super stable. I mean, luckily for us, they're, it's not, I don't want to compare it to launching a space telescope because I know that I'm in the wrong place to be bragging about something like that, but it feels a lot like that because you drill into the ice and you put them there and there's no easy way to take them out. So there's no repair for the sensors that you deploy. And this, assuming that will keep the ice at the South Pole frozen for a long time, those should be there for tens of thousands of years, perhaps. That's the age of the ice at the South Pole. So the only thing that actually kills the sensors is actually power cycling them, because sometimes there are some sensors they have small computers in them, and like with any computer, if you power cycle things enough, you have a probability that in one of those power cycles the computer will not come back, and there's nobody to press a reset button to go down there. So that's how we've lost some sensors. But out of the more than 5,000 we have deployed, we have lost a tiny fraction in much less than 1% in 10, well, now 12 years of operation. So things are looking great, and it's likely to, I mean, the health of the instrument is not an issue, fortunately for us.
And I would imagine that, and this is piggybacking on another question here, I would imagine that drilling as far down and setting them up in the way that you do, climate change / like ice melting, that sort of stuff, is not an issue because of how far down you're going.
Exactly.
Yeah.
If there's any issue, is that the glacier itself is sliding. I mean, at the South Pole, you're still on top of a glacier, and that glacier is moving with a speed of about 10 meters per year. So the whole thing is sliding sideways, and the South Pole station as well on top of it. But the thing is that if there happens to be shear between different layers of the ice, for instance, the ice, remember that the detector itself is 1 kilometer tall. So if there's a slightly different pace of, let's say, motion between the bottom and the top, that could lead to the cable snapping at some point. So I think that that's the only risk, but I don't think we are anywhere close to that being an issue, because most of that ice moves as a solid block, as most of these glaciers do.
So in doing so, it wouldn't affect the majority of your science or your instrumentation.
That's right, because it just moves a little bit to the side, and then we keep track of the geometry of the detector. We have light sensors where each one of this light sensor is also kind of its own disco ball. It has LEDs on it, and then we make them flash. And when we make them flash, we record the light that is seen by the other sensors. And since we know the speed of light, you can know, I mean, if you know when you emitted the pulse of light, and you know how long it took the other one to record it, you can know the distance, right, between any two sensors. And if you have this three-dimensional object, you can do a lot of math to figure out how far is each one with respect to the other, and figure out the geometry of the telescope. And that's actually what one of my colleagues at the University of Alabama does, which is the calibration of the geometry. And we have we keep good track of that too.
You just answered the question I was about to ask, and I could see it all. I was like, I'm thinking about, with electromagnetic doing flux calibrations and flat fields and knowing all the details about your instrument. It's just a different way of doing it. Yeah, I think. Yeah, IceCube is such a creative experiment to be able to do what we need to do to get the very small number of detections that we're finding. And one of the things in the beginning, I think you said, there's, through your lifetime, I believe was the statistic that you have a 50-50 chance of one neutrino potentially interacting with your body. Right. Is that correct? Okay.
Yes.
So what would happen if a neutrino did interact with your body?
That's a good question. So luckily, the neutrinos that go through us have low energies in terms of this, like 1 million times the energy of visible light, but still that amount of energy is very, very small. On top of that, it's not that the entire neutrino energy is dumped into the body. It's just a tiny fraction, perhaps 1 keV, a few kill electron volts. So at most there will be like just one single X-ray, not an X-ray like an X-ray that we do to look at our bones, but a single photon, an X-ray photon going through our body once in a lifetime. There are many more X-rays that we are exposed to from things around us, and also going to the doctor. So that's not an issue.
Yeah, I know the general public always wants to know, should I be worried? So now I can tell them, no, you don't have to be worried.
Unfortunately, it would be great if we could detect neutrinos more easily, and it was a problem, but they go through us, so it's hard. That is a problem.
All right. Well, I've got two more, and I think given time, I think we'll finish off on two final questions.
Sounds good, Grant.
One follow-up and one new one. So will there be an IceCube phase 3?
Ooh, I would love that if there could be an IceCube phase 3. When IceCube was built, its predecessor Amanda was also there at the South Pole. It's a much smaller version of IceCube, and it was IceCube was predicated on the fact that Amanda was not big enough to see astrophysical neutrinos, and he never saw astrophysical neutrinos, and there was a good reason for that. So IceCube was built saying, this is the one that will actually see the astrophysical neutrinos, and we got that. Now the next thing is, okay, now we have the astrophysical neutrinos, we need more neutrinos to see sources and do real astronomy with them, like measuring fluxes like you do in astronomy, getting spectra for sources, getting things like this in neutrinos, not in light.
The more you found, the more you needed. Exactly. Science.
That's we're greedy. We're greedy. So once IceCube Gen 2 is operational and hopefully sees plenty of sources, I think it will determine also what the next generation telescope will look like in terms of what we can see and what we can learn from these observations.
All right, and I'm going to finish this off with a follow-up from the gentleman from earlier. Are the detectors basically photomultiplier tubes? And could light avalanche diodes be more efficient in capturing?
Very good question, very technical. Yes, PMTs, photomultiplier tubes, are the ones that we use. And the photomultiplier tubes are good because they, think about it in terms of an inverted light bulb. In light bulb, you run current through it and it emits light. In this case, you have a photocathode that is a photoelectric material that whenever you have a photon hitting it, it produces an electron. So it produces a little bit of electricity. And we have a way of multiplying that electricity, that electron, into a signal that we can measure. Okay, so these photomultiplier tubes, these PMTs, are very good because we can build them pretty big. And therefore, any photon that hits the PMT across the entire surface of the photocathode will result in a signal. And since these sensors are separated by tens of meters with respect to the next one and 125 meters horizontally from the other one, you want a big area for your photosensors so that any photon that is produced by these muons actually creates a signal. So that will be much more difficult to do with any kind of silicon-based detector, because silicon-based you can only build them so big. And if you wanted to build a gigantic surface, it will be extremely expensive. Each one of these photomultiplier tubes that we have, the sensor itself costs about between $1,000 and $2,000. But if you have to deploy 5,000 of them, that's a lot of money. Perhaps not JWST money, but still a lot of money. So we could, but it's just not economical to do so. But we're still looking at different technologies for Gen 2, perhaps have a segmented PMT that can reconstruct also where the light was coming from and just not tell you, yeah, I saw light, that's it, but also where the light was coming from.
One day.
Great.
Yeah. One day.
Well, thank you so much, Marcus, for
thank you. This was
joining
a great
us
pleasure.
For this public lecture series. We learned a lot about neutrino physics and understanding how we can uncover more details about astrophysical sources. I encourage everybody to go out and follow, like I just did. I just followed the IceCube Neutrino Observatory so I can hear what's going on down in the South Pole, and looking forward to sharing and looking at that app as well, because since there's so few, knowing which ones are coming through it's important to us.
That's right.
We can give them all all names, right?
That's
well, thank
right.
you again.
Thank you very much.
Thank you to those of you who are listening in real time. Keep an eye out for next month's public lecture series with Dr. Frank Summers talking about Eta Carina and some great visualizations, I'm sure, that he will be sharing, and sign up and get announcements for our future talks. So thank you and good night to you all out there. Bye.
Good night,
Bye.
everyone.